Welcome to Wednesday afternoon at SDC. If you're here, you are one of the diehards that hasn't snuck out early to beat the traffic. I hope you're not overselling us here. It's a pleasure to be with you. My name is Ace. I work for Solidigm, and I'll introduce you to the company in just a minute if you don't know who we are. I've been with Solidigm since it was born, almost 4 years ago. Our birthday's coming up. And I work in the Sacramento area, a couple hours up the road. Solidigm, for those who are not familiar, was born when Intel sold its non-volatile memory business to SK Hynix. That created a US-based subsidiary, which we named Solidigm. It is wholly owned by the SK Group and SK Hynix, but it is US-based in terms of there's a US leadership team, US CEO. In fact, we have 2 US CEOs, because everybody knows twice as many CEOs means twice as great company performance, right? We, in our history, have made both consumer and enterprise SSDs, but these days we focus exclusively on enterprise storage devices. We're going to talk today about retrieval augmented generation and a key problem with it, specifically that it's too good and too popular at the moment. It's outpacing the infrastructure that's built to handle it today. And then we're going to talk about some work we've done internally with a great partner called Metrum AI. They're experts in the agentic AI space to put together different approaches to running inference workloads with RAG and moving some of that data out of HBM and out of system memory into NAND, see what happens. We'll talk about an example workload where we used that approach and key findings. Okay. So this is RAG. I suspect most in the room are familiar with RAG. We've had a lot of sessions on RAG this week, but I did get a request from our show organizers to please explain what RAG is. So this is the primer. If it's a new term, we'll go through it very quickly. So if you are doing inference in a very basic form without RAG, you get what you're looking at here. So there's a query or an input at the beginning of the process that gets fed to some kind of a trained model. That model is aware of the entire universe of data that was part of its training data set and nothing more, which is a static data set locked at some specific point in time and then used to train the model. And if that universe of information from the training data set is sufficient to give a meaningful answer to the user query, you get the green bubble, you get a correct response, right? If that training data set does not in fact include the data that's needed to give a meaningful or a correct answer to the response, you either get no response, sorry, I can't help you with that, or worst case, you get what's called a hallucination, right? Where the model confidently asserts an answer that's completely wrong. And if you've played around with chatbots for any length of time, you may have experienced that yourself. Where RAG comes in is it makes additional data accessible to the model that you're querying, right? So now, rather than only being able to see and use data that was part of the initial training data set, AI models have the capability in a RAG framework to consult external data sets, which can be dynamic, which can be updated far more often than you might want to go through the trouble of retraining the model, right? And so in a RAG-enabled inference type use case, your user query initially goes to the additional data that's available in these RAG data sets. The query is vectorized, it's compared against embeddings that were generated from the data in the RAG set. There may be an internet search component to that as well. That's more and more prevalent these days for especially public chatbot type applications. And then what the model ends up seeing is not just your initial query, but it's a combination of your query plus the relevant data that was retrieved. That's the retrieval part of retrieval augmented generation. And it's used to generate a better answer. The idea being you get the green bubble more often and you get the yellow and the red bubbles less often with RAG, right? Pretty straightforward. There's a lot of nuance here, but high level, that's kind of the value prop. Why do we say there's a problem with RAG? This is an example we've used recently to sort of describe what's going on in the RAG landscape. That's a picture of a very famous music festival called Woodstock that took place some years ago, and is famous not just for the incredible lineup of acts that were there, right, but is also famous for the many, many stories coming out of that from attendees about how the insufficient infrastructure, the lack of infrastructure at the show made for a dirty, muddy, messy time for most folks. I don't recall the numbers offhand. The organizers had prepared for something like 50,000 attendees and gotten something like 300,000 or 400,000 attendees. Some multiple of what they had planned for, and so you had this incredible product that people were excited about, that they wanted access to. They wanted to hear Jimi Hendrix. They wanted to hear, the Doors, everyone else who was at Woodstock, but because of infrastructure challenges, the stories they came away telling were more about sanitation problems and messes in the mud and this kind of stuff, right? And so this is an experience that we are hearing from customers is taking place more often with RAG now as well. They're really excited about the notion of connecting their models to bigger and bigger data sets for inference to get more and more meaningful answers, higher quality insights. But the challenge is there's a cost associated with all of that, right? With storing that much data, with accessing that much data real time, with sort of optimizing where it's stored and how it moves around inside of an AI cluster in terms of tiers of storage and memory. And so while the value prop is clear, how we get there and how we optimize the infrastructure to make sure everybody gets a good experience is an ongoing discussion. So Solidigm asked the question, what if we could move significant amounts of AI inference data out of GPU memory, and I'll add system memory as well, to lower cost NAND SSDs. This is our little infographic here, our attempt to kind of illustrate what's going on, right? In a conventional RAG-based approach, you're trying to keep as much as you possibly can in memory, which makes life hard, right? It gets very expensive very quickly, particularly when you're looking at these bigger RAG data sets. So if we were to use some of the open source available approaches out there to offload some of that to NAND, what would we gain and what would we lose? And that's the question we posed to our partners at Metrum AI. Did some great work with them earlier this year. And I'm going to walk you through kind of how we set up the experiment and what we learned and where we go from here. So how do you do that? How do you offload AI inference data that's usually in memory to NAND? What are the tools and techniques that are used? Primarily, we relied on two, and you've probably heard about at least one of these in several sessions this week. DiskANN has been the topic of a couple of great presentations. My colleague Alessandro gave one yesterday, I think, right? Monday. And Wes from Micron also talked about it this morning. So this is an open source suite of algorithms originally developed by Microsoft for use in their Bing search and their Microsoft 365 applications. But it allows large-scale vector data searches. ANN stands for approximate nearest neighbor, and that's not novel, right? That's done in the conventional approach as well. But what's novel about DiskANN is the disk part, which permits us to relocate part of the RAG data set, specifically the vector index, from where it usually lives in system memory to SSDs. And so we use that. And then the other half of the experiment was about model weights specifically. So if you're using a given model, generally there's associated GPU memory requirements with those models. Can we offload some of that stuff that typically lives in the high bandwidth memory on the GPU into SSD-based storage And what would that buy us? What would that look like? And so to accomplish that, we used a couple of additional pieces here, RayServe, and then another Microsoft component called DeepSpeed, which typically has been used on the training side of AI. So this is a little bit of a less common application of DeepSpeed technology, but we use that to see, okay, so we don't need to keep all the layers of the model in HBM at all times. We're only accessing certain layers at certain times. So can we offload the other stuff we're not using to non-volatile storage, which is a lot less expensive. So that's kind of the two halves of the experiment, offloading the RAG vector index and then offloading some of the model weights themselves. This is kind of the stack that we built with Metrum AI. I'm not going to go through every box here, but there's a few key pieces that I do want to point out, and this will make more sense when I show you the example workload in just a minute, and how we kind of put together a demo to illustrate the approach here. But fundamentally, we've got 3 models involved in our example workflow that I'll go through. We have a vision language model, we have a model for generating embeddings, and we have one, the Llama 3.3 70B model for large language. And I'll show you how and why we're using those in just a minute. But the idea is loading all that vector data into Milvus, which is a vector database that supports DiskANN, offloading the model weights using DeepSpeed. And this was kind of the underlying hardware that we ran our experiment on the bottom as well. So we had our kind of Gen 5 performance-oriented TLC SSD, the PS1010, and we used NVIDIA L40S GPUs. Why the L40S? Well, because we wanted to pick something with a smaller GPU memory budget, right, and see if we could fit big models into it and see what would happen. Okay, so this was the kind of the source video for our example workload that we did some of our pathfinding on. We chose a kind of a traffic safety use case. So this is a video that's about a minute long. There's all sorts of things going on at the intersection. You got cars, you got pedestrians, you got cyclists, and sometimes in the course of the video, these things are avoiding each other and behaving in a safe manner, and sometimes they're not, and there's some close calls, right? But the idea was, can we feed this into an AI pipeline, the outcome of which is a kind of a text-based safety report that says, hey, here's the things you can do to improve safety at that intersection. But in the course of doing that inference work, we were to rely on these SSD offload approaches for some of the data involved in the workload. We built a dashboard, and I'll highlight this later, and I'll show a link later, but if this is something that ends up being interesting to you and you want to kind of kick the tires on it yourself, everything you're seeing here is available on GitHub. It's built on open source components. All our documentation is there, the source video, the dashboard, the underlying components, and any kind of customization that we did to those pieces is all there. So please do check it out if it's something that's of interest to you, and we'd love your feedback. So this is you know, sort of the UX piece here. From left to right, in the top left is where a user can upload a video. So in this case, we're talking about that traffic intersection video, right? And then when you hit run or begin analysis, you're off to the races. And a few things happen over the course of the 5 steps that you kind of see in the top center part of the dashboard there. So in step 1, we're ingesting the raw video file. In step 2, we're summarizing the content, and I'll go ahead and overlay some of the models we used here. So in step 2, we're using the Phi 3 vision language model to generate frame-by-frame text descriptions of what's going on in that intersection video. In step 3, we are creating our RAG database. We're generating embeddings based on the content that we ingested. And in step 4, finally, we are retrieving those embeddings and building out our insights, in this case, kind of the traffic safety report, right? And you can see there's other things going on the dashboard that are interesting. Kind of the center bottom part of the dashboard there gives you some kind of I/O key stats. For the drives in the server, what are the read and write bandwidths? How heavily utilized are the drives? Temperature and so forth. That stuff updates dynamically as the workload runs. And then on the right-hand side, you can't see all of it because there's a bit of a scroll, but there are some key kind of GPU utilization metrics, some key metrics that express the effectiveness or the success of this approach in terms of metrics that the AI experts really care about. So things like tokens per second, right? So that all gets generated on the fly as you run this as well. And then in the top right, those purple boxes, those are toggles. So we built the dashboard in such a way that you can turn off the vector DB index offload and run it all from memory and see what results you get. You can turn it back on and see the results with the SSD offload. And then the second one, it has to do with the model weight offload. You can turn that one on and off as well. So we ran this several times, and I want to share key findings that came out of not just the example use case we're talking about, but we also ran some more general kind of vector DB bench type testing to understand the impact of the SSD offload approach, the DiskANN stuff on some key metrics. So the first thing that we learned was that the Llama 3.3 70B model is big, right? Recommended VRAM budget for that is 161 gigs if you're running this at FP16 precision. Clearly that wouldn't fit on an L40S if it was deployed in a conventional way, right? But using the SSD offload approach where we move model weights to SSD, what we found was that the highest DRAM utilization that we saw here for hosting the model on the GPU was about 8 gigs. So all of a sudden, this combination of a particular GPU and a particular model that don't fit together, don't work together under a conventional approach, now are usable together in a way that wasn't before. And that's specifically enabled by the data offload of the model layers to SSD. We also saw, in terms of some of the vector DB bench testing, we're talking now about system memory, right? The model weight comment was specific to HBM, but now we're talking about the DRAM outside of the GPU. We ran tests at different vector database sizes to kind of see what the impact would be. Intuitively, we expected a result where if you're moving more data to SSD, you're using less DRAM, right? There's nothing shocking about that assumption or that hypothesis. And in fact, that is what we saw when we ran these tests with and without the SSD offloading approach. So the difference in DRAM utilization grew as the size of the data set grew. Again, intuitively makes sense, right? When you're talking about a 1 million vector data set, we're more or less on par in terms of how much DRAM is being used. But as you scale to 10 million and 100 million vectors, all of a sudden, you're using meaningfully less DRAM, right? Which is, from a cost perspective, is an important thing to understand. There's a big cost difference per gigabyte between system memory and NAND, of course. You might look at this and wonder, okay, well, what are the trade-offs I'm making here? It's great to be able to say, this inference approach uses less DRAM, but what are you giving up in terms of, for example, performance? And this is where the results that we got were a little bit counterintuitive. Were not necessarily what we expected to see. In fact, across a number of our tests, we actually gained throughput in terms of queries per second when we offloaded that RAG data from memory to disk. And you ask, well, how is that possible? How does that make sense? Anytime you move something from DRAM to NAND, you're going to lose performance, right? And your latency is going to skyrocket. We tested and retested. We showed this to various internal forums who said, no, there's a problem with that data. Clearly, you guys screwed up the test. You need to go back and rerun. But in fact, we ran it a number of times. And after internal review and sort of exploration into the indexing algorithms, we emerged with confidence that these numbers are in fact accurate. I won't go into great detail about why that is here. Alessandro gave an incredible session on Monday talking about different vector search algorithms, talking specifically about DiskANN and what's going on under the hood in terms of how the Vimana indexing algorithm used by DiskANN does things a little differently than the conventional HNSW approach. But suffice it to say, it's incredibly efficient at packing a lot of data onto an SSD in a way that when you're running inference real time can actually accelerate your QPS, depending again on your data set size and other factors. So translating that into some of the, again, some of the metrics that our sort of AI outcome-oriented friends are more focused on, this was what emerged from our testing in our lab in terms of what we spent on the hardware and what we saw in terms of performance and performance efficiency. So looking at the results from the 100 million vector data set, using the conventional approach, we got about 126 QPS and spent about $3,500 on the combination of memory and storage to accomplish that, right? Using DiskANN, we gained performance. We spent significantly less on the DRAM. So you can see there's about a little over a 2x improvement in terms of queries per second per dollar as a result of this approach. If you're still skeptical and still wondering if there are trade-offs associated with this approach, that's fair, and there is an important one that I will talk about in just a minute. But accuracy is not it. Accuracy was another thing that we saw. Consistency across the board, different data set sizes. The recall was high quality, whether you were using the conventional HNSW approach or whether you were using DiskANN. The important trade-off with this approach comes in the higher indexing time up front, right? So there's no free lunches here. This is not an exception to that rule. We're using less DRAM. We're at least maintaining performance parity and in some cases squeezing a little more performance out of this approach. But in terms of the way the Vimana algorithm that's used by DiskANN does the upfront work to build the vector index does take significantly longer than the HNSW approach. This is something typically you're not doing as often, right? So it will matter on a case-by-case basis how painful this is and how much that trade-off is or is not worth it for a specific customer or a specific application. But it is important to call out that this was one of the areas that even in our testing was fairly painful, right? To build these indexes, to be able to test them took, in some cases, hours and hours and days to do that. So something to keep in mind. I promised a link here to be able to kind of check this out if you're interested. Again, this is not a Solidigm product. This is not something that we are monetizing, right? It is an experiment built on open source components that we think some folks may find some value in, and we hope others will be able to build on this and go do even cooler things with this same kind of philosophy. And I'll talk about some of our next steps and what we have in mind to test in our lab next, but would absolutely love to hear from anybody who finds any value in this or wants to point out any alternatives to this approach, because ultimately, we're all in the pursuit of optimizing TCO and efficiency in AI clusters. It's not an easy thing to do, as we saw with our Woodstock analogy up front. Okay, so where are we heading from here? Where do we think the next few interesting stones to turn over are? One has to do with QVS. So QVS enables GPU accelerated building of vector indexes. And that's a promising new technology. The newish wrinkle, I think they presented about this at GTC in the spring, is that they now support, if you're using Milvus, they now support GPU accelerated index building with DiskANN as well. So this will be something that we're excited to explore, to see if, you know, the one kind of major pain point or trade-off involved in this approach, which is the index build time, gets any better using QVS GPU accelerated indexing. That'll be something we'll keep a close eye on, and certainly update the white paper and publish new results when we have them on that front. We're also from here going to be going into more complex, more distributed workloads. For our first pass here, what we're calling phase one of this work, it was essentially all inside of a single compute server, right? We had GPUs in there. We had Gen 5 SSDs direct attached to those GPUs. We know that's not how a lot of this is occurring in the real world, and that a lot of this RAG data in particular will be found over the network on dedicated storage servers. So what role does that play, or how might that affect our results, will be things that we will go and go off and explore as well. And then finally, and Alessandro talked about this a little bit earlier, there's an opportunity in the marketplace to go off and work with some of these VectorDB folks on support for DiskANN, because right now it's pretty limited. Among, you know, the big database types that folks use, there's not a lot of ability to, even if you buy this approach and the trade-offs make sense to you, you're fairly limited on what you can actually deploy to realize some of these results. So that's an effort that Solidigm is undertaking now, again, working with partners to try to understand, okay, if this is an approach that has value for folks, that makes sense for a lot of use cases, let's figure out how we get it enabled more broadly across the ecosystem. Okay, key takeaways here. So one of the things that we learned in the course of our experiment was that you don't need to spend necessarily an astronomical amount of money on DRAM to scale your inference data sets, your RAG and your models. In some cases, that will continue to be the best or perhaps the only path forward, but there may be applications out there where this kind of SSD offload approach makes a lot of sense. And as we saw from our VectorDB bench results, there are potentially significant savings to be realized in terms of the amount of memory being used to host a lot of this inference data. We also learned that being clever about how you build and use these vector indexes can not just save you money on DRAM, but there are potentially cases as well where cost-efficient performance goes up in terms of that QPS per dollar metric we looked at earlier. And finally, there's more to learn here. We're in the very early days of this. I heard somebody on a panel Monday say that like the two key areas of opportunity for storage and inference today seem to be KV cache offload and RAG data offload, and I think that makes a ton of sense. There was a great presentation. If you missed it, I encourage you to check out the video by someone at Dell about the KV cache offload stuff. Really good presentation. We're talking about the other half of that opportunity here, right? But there's much, much more work to do to understand you know, how much this hunts across how broad a swath of use cases, you know, how the trade-offs change depending on the levers you're using in your particular application. So please do stay tuned. We'll be publishing more work on this, of course. And if folks are interested in getting involved and either digging into the results more or potentially doing some work together, we'd love to hear from you on that front as well. So with that, I'll go ahead and wrap it up. And how are we doing on time for questions? We're good? Okay. Awesome. All right. Yeah, please. Thank you. Excuse me.
I was confused about when you compared the without offloading versus DRAM. So the DRAM you meant was DRAM class M40 chip. Or do you mean any CPU based?
There's a couple of things going on here. So sorry, I'll repeat the question. So the question was when we're talking about the amount of DRAM we're using and the differences that are created as a result of this offload approach? Are we talking about system DRAM or DRAM on GPU, or where is the memory we're talking about? Is that right? Okay. So we're actually talking about two different places where we might optimize memory utilization. When we're talking about the DiskANN stuff and moving the vector database index from memory to storage, we're talking primarily about system memory there. So that's the DRAM in the box. When we're talking, yeah, that was this one here. So your DRAM usage with and without SSD offloading is here. And this is I could have been more clear on this. This is focused on the system memory here. And so in the example of the 100, DRAM on the SSD, we're not talking about that. We're just talking.
I'm not talking about that either.
Okay.
I'm saying this DRAM, which you said is the CPU's DRAM.
Yes, it's CPU attachment because search only happens in the CPU.
Yeah.
What happy to have you talk, but if you're going to, sorry, help me. Just go here with.
Yeah, I appreciate it, Alessandro.
How much CPU DRAM was there in my system?
Okay, so the numbers are on the top of the bars there. So for example, in the 100 million vector data set, that was 336 gigabytes of DRAM without SSD offload, moving to 145 gigabytes with SSD offload. Does that answer the question?
That is the usage, right? Not the amount of data actually on the system.
Correct. Yep. That was the active usage in the course of running the workload, which implies under this approach you may be able to get away with loading less into the system in the future, right? That's kind of the idea. Yeah. Stephen, I think I haven't been in a session where I haven't seen you ask a question. You always got the good questions.
I don't know if this one's a good one. So that 100 million vector data set, like how big is that as a binary?
Oh gosh. I don't. Yeah, I don't recall off the top of my head. I'd have to go. It's in the white paper, which is in the link I provided. It's a good question, but I don't recall offhand.
It seems like, I'm going to assume it's like, say, a kilobyte per vector. Maybe, I don't know, I could be wrong. Put that at about a gigabyte of total thing. But if only 300 is loaded, I'm trying to get a sense of, what is the working set in the DRAM versus stuff that isn't? Or do these frameworks put like all 100 million in their entirety in DRAM?
So what we have moved here specifically, this may or may not specifically answer your question, but what DiskANN enables under sort of its prescribed approach is not relocating the vectors themselves from memory to storage, it's the index. You may have seen things like Kioxia's AI SAQ, I hope I'm pronouncing that right, where they took DiskANN and they basically said, what if we tried to use little or no DRAM, right? And so I think they're actually offloading a lot of the vectors as well. So there's sort of a Venn diagram between our two approaches. They've done some very cool stuff, by the way. I'm really psyched about what they're working on. They were a little more aggressive on the RAG stuff, and we went a little more into the model weight offload stuff as well that wasn't covered in their approach. Yeah, please.
What you've done kind of mixes the effect of testing one algorithm against the other, and then you're kind of inextricably mixing that with the DRAM versus the flash. So an interesting test would be, instead of using flash, put it in a RAM disk, something like that. So you get you tease out the algorithm efficiency differences from what you're then getting back. And obviously, you make a great cost of it. I know it's been true since 2018 when they wrote the paper. It would still be interesting to kind of tease out what you're getting out of that.
I think you're spot on. There's a lot of additional work to do here, and getting more modular with the pieces of the solution would be really interesting, right? To understand really what's the effect of.
Yeah, you got Alessandro here. You can do that this weekend.
Yeah, he doesn't mind. He doesn't have plans. Good comment. Thank you. Any other questions? Okay, thanks a lot. If this was interesting to you, please do check it out on GitHub or the white paper on solidime.com. Check out the video of Alessandro's presentation if you weren't able to attend. Wes's presentation this morning also talked about DiskANN. It was a very insightful, informative one as well. So lots of good content here at SDC on this topic, and expect to hear more from us going forward. Thank you.